Hey everyone, today we're looking at the paper WT5, Training Text-to-Text Models to Explain Their Predictions by a bunch of authors from Google Research. This paper is about text-to-text generation models, and in particular about making them explain their predictions, as the title suggests. So the authors start off by talking about the text-to-text pre-training framework proposed by Raffel et al. A couple of months ago, which is a great approach for pre-training these text-to-text generation models on large unlabeled sequences by using different noise objectives. So the way this works is you are taking, let's say, a lot of sentences from raw data and then doing perturbations to those, like masking tokens, deleting or shuffling, for instance, different types of perturbations. And pre-training on those type of denoising tasks resulted in really nice pre-trained models that can then be used for downstream tasks like summarization or different text-to-text problems. So we've seen large advances in these text-to-text pre-training approaches, and these authors actually tackle with a slightly different issue, the explainability of these text-to-text generation models. And in particular, what they propose is a framework for making those models generate explanations without making any changes to the model internals. This is the same sequence-to-sequence scenario. And in a standard setting, one way you could be using these models is, for example, to train a sentiment classifier. Let's say you're given a sentence: I went to see this movie with my husband and we both thought the acting was terrible, and you want to predict that the sentiment is negative, so we didn't like the movie. But what the authors do is they actually have a special case in the training data, special cases where they want to generate an explanation in addition to this sentiment prediction. So the way they do it is they prepend a special explain token to the input explain sentiment in particular. So they want an explanation for the sentiment, and they want the model to generate the correct sentiment negative, as well as a special explanation token which is reserved for this function, and then an explanation for this, which is here the acting was terrible as the reason for the negative sentiment. And the way they do it is they fine-tune these large text-to-text transformers, T5, they're called T5 actually in this paper. They fine-tune them on some datasets constructed to have these explanations included in them. And they call their model WT5. Funnily. So they use a bunch of datasets that already have such explanations available. So there's a few of them already, some of which have already been used to train such models to generate explanations of themselves. For example, one dataset that they use is this SNLI, which is a natural language inference dataset, which comes with free-form explanations of the labels. So this is a classification dataset, and the explanations can be used to try to investigate whether the model can explain the output. They also use so in this case, this dataset is coming with abstractive labels. However, there's a bunch of datasets which come with extractive labels. So for example, we have this COS-E dataset, which is a common sense question answering, where you're given some question and you have to come up with an answer without having any access to any knowledge base, let's say. You also have some movie reviews which have a sentiment. You have some really comprehension dataset, and so on and so forth. But apart from the abstractive explanations, part of this natural language inference dataset, you also have extractive explanations, which is the case for the example we looked at before. So in this case, actually, the explanation, the acting was terrible, is part of the input. So you just have to figure out and copy over the span of text from the input to the output, which is best suited to explain the negative sentiment prediction here. So this is their scenario, and they basically use the pre-trained T5 models, and then they fine-tune on these datasets that have the explanations, constructing suitable fine-tuning datasets by appending these explain tokens that I talked about, the special tokens. They actually use two variants of the T5 models. One is the T5 base, which has 200 million parameters, and they also a T5 11 billion, which is a much larger one. So let's look at some results of this fine-tuning on the explanation benchmarks. So in this table, we have three metrics. We have the classification accuracy for, because all of those are pretty much classification datasets, I believe. And we also have a blue comparing the basically some n-gram overlap, or like n-gram precision-based overlap from the system-generated explanation to the real explanation that comes with a dataset. And we also have some human evaluation scores of the quality of the explanations for the human-generated explanations, as well as for the big WT5 model. So what are the results? It seems that the WT5 base and the big one in particular outperform the previous state-of-the-art, as well as even the human-generated explanations across those different benchmarks. You have the movie reviews, the MOTRC. This is the, I think that was the reading comprehension one, COS-E, and so on and so forth. In terms of human evaluation, quite often, as well as blue scores here. So it seems that this T5 pre-trained model fine-tuned on this dataset works much better for this task of generating additional explanations. So it seems that leveraging this models pre-trained on large amounts of raw data really seems to be beneficial somehow for this. Perhaps even on the decoder side, you're able to generate better explanations because this model has been trained to generate different texts of different sizes. So this is one interesting result. It's interesting that you can outperform the human as well. And some other interesting experiments are regarding transferability of the results when you haven't trained on the same dataset. That is one experiment that they do. They hide one part of the training data. Let's say you have two datasets regarding sentiment of movie reviews. Let's say you have some Amazon reviews, and then you have some IMDb reviews. So what they do is they train only on one of those datasets, and then they see if their approach can generalize to the new dataset, which might contain slightly different reviews, slightly different style than the other dataset. And it seems that you're capable of preserving the accuracy. Sometimes I don't remember the precise number here, but I remember reading that this kind of works, so you're able to preserve across the datasets. Then finally, probably more interestingly even, is transferring across tasks. So in this scenario, they actually don't just transfer across datasets in the same domain, but even across tasks, different tasks. And here in particular, what they do is they fine-tune a model only on the ESNLI dataset, which is the inference dataset. And then they test on the COS-E dataset, which is the open domain question answering dataset, to see if you can still generate reasonable explanations without having seen this one. So actually this is quite a big gap between the datasets, and this is kind of like a zero-shot explanation generation. And obviously this will work worse than when you have fine-tuned on this COSI dataset, but here we have some examples cherry-picked from these experiments, and it seems that sometimes it works. So let's say you're given a question, when going to sleep, what happens to your body? The predicted answer was relaxation, and the explanation was, when going to sleep, your body goes into a state of relaxation. So this is quite a good explanation, and it's cool that you can generate this without having trained on this task. And this again probably highlights the power of pre-training these models, because so pre-training on the dataset in the beginning probably helped to come to this more fluent answer, which even though like generating this more fluent explanation, even though the model hasn't been trained on this. That would be my guess. So that is all that I wanted to cover for this paper. It's an interesting approach to leveraging large-scale pre-training data and fine-tuning on some datasets for explanations without any modifications to the architecture, to be able to come up with an approach to generate explanations for model predictions. One obvious limitation to this approach that also the authors comment is that the explanations are in general obviously quite surface level, in the sense that they basically relate more to the training data itself, rather than they don't really tell you maybe in super detail why the model itself decided to generate a particular prediction. They just kind of relate, okay, which parts of the inputs or which texts are most useful to generate a good explanation, which might increase the blue score basically at the end of the day, right? So this is one potential limitation, but obviously this is a good step forward towards coming up with models that are more explainable and more intuitive to humans. So thanks for watching. Please like and subscribe for some new upcoming NLP content coming out hopefully every week on this channel. Thanks.